perception of the real. Yes. Mathematics involves a lot of that from the beginning. That's what happens. You perceive your real environment. For example, you may see a car moving, and then you may be thinking in your mind, quantitative mental thoughts using words. And it goes, I saw a car move a distance of 200 meters in 10 seconds from left to right. So that could be something you actually perceived, all right, in the real world. Objectively, that's what you perceive using your, your eyesight and your auditory, senses, because you may hear, and you even probably may, your olfactory senses, you may smell the fume and so forth. Therefore, the velocity of the car must be 200 meters in 10 seconds in the positive direction, moving from left to right. Okay, so perceiving the car moving, and then here you have those mental thoughts using words in your mind, and you may even write it down, okay, using words. But then now, to facilitate the analysis, the quantitative analysis of this whole real phenomenon, you may quantitative written reasoning using graphs and symbols. Okay, so here you have a graph, and it shows you from 0 to 10 seconds, you saw the car move from its reference point from 0 meters to 200 meters in 10 seconds. And you can further the analysis by changing distance to d, positive to a plus 200 meters. As you can see, the symbolic written form, t for time, 10 seconds, and the velocity is 200 divided by 10, a positive 20 meters per second. So you can actually see from the real phenomenon to symbolic form. Okay, and mathematics to facilitate quantitative reasoning, written reasoning. So mathematics can be viewed, in that perspective as a language, because you can see the translation from words to symbols. Okay, from the real to words to symbols. Yes. So now mathematics brings to the table this process. First, we may perceive our environment, we perceive reality by seeing, hearing, smelling, tasting, feeling, intuiting using the sixth sense. And then in the mind now, we are thinking words according to the native language. If you speak English, you will think English. If you speak French, you will think French. If you speak Latin, you will think Latin. If you speak Spanish, you will think Spanish. Two general forms that will be happening, qualitatively and quantitatively. Qualitatively, we'll be using a lot of words, right? And that's what we the majority of the time, that's how we analyze, using qualitative and using words. And the quantitative category is normally suppressed. Colors, texture, aesthetic, beauty, and so forth. That's qualitative reasoning. And quantitative reasoning, you want to analyze most likely the height, the width, how many of the item that you are viewing or the object, the cost, the temperature, okay? And that's quantitative reasoning. And they are both involve communication using words. And but in the quantitative arena, most times, the majority of the times, if not all of the time, the words are converted to symbols. Okay, so we can see that in a little while. And we saw that a while ago, the words converted to symbols. So what happens now, we imagine after we perceive the reality, we think using words, qualitatively and quantitatively, then the abstract that we imagine, we want to socialize, we want to communicate. Socialization means communication that requires spoken and written language. So the qualitative reasoning using a lot of words, writing words, and the quantitative reasoning translates words to mathematical symbols. So that's why mathematics can be considered first. You start when we objectively perceive the real world with the five senses. Then in order to communicate the subjective abstraction of the mental image that was formed in the visual cortex and other areas, we design diagrams and graphs, as we saw a while ago, and also convert words to symbols. Very often that happens. In that way, we facilitate the documentation, thus the written communication of ideas involving numerical analysis. Yes. For example, the famous plus sign. Okay, the origin of the plus sign is credited to the 14th century French mathematician named Nicolas de Racem. When he was writing his book, he found himself having to write the word et over and over. Okay, you have tria et quattro Achelia sunset, that's Latin. Trois et quatre égale sept, that's French. 3 and 4 is equal to 7. Okay, Latin, French, and English. These are words. Okay, we can look at the translation. We can look at the translation in French. 3 and 4 is equal to 7. Trois et quatre égale 7. Okay, and the Latin translation of 3 and 4 is equal to 7. Okay, you have Tria et quatorze égale 107. Okay, so you can see the whole idea of words now. When we are thinking, we're thinking words. And these words now will be converted to symbols, because instead of writing et every time, he therefore then replaced the word et with the letter T. And the T now evolved into the symbol that we now know as a plus. So that's the origin of our plus. Again, to emphasize the whole idea of a word turning into a symbol. Words to speak, et, symbols to write, the plus sign. And just take note that in arithmetic, the word and is plus. Always remember that. If you say 2 and a half, you are saying 2 plus a half. Okay, we know the mixed number 4 and a quarter. That will be like 4 plus a quarter. Okay, so never forget that. The equal sign, the origin of the equal sign is credited to the 16th century mathematician named Robert Recorde. When he was writing his math book, he found himself having to write it was is equal to over and over. Tria et quattro égale 107. That's Latin. Trois et quatre égale 7. French. 3 and 4 is equal to 7. English. Words. Okay, as you can see, words. Égale égal is equal to. He therefore replaced the words is equal to with 2 horizontal parallel lines of equal length. So you can see the words to speak, and we have to write all these letters, égale, all of that. You can just replace all of this in a symbolic form, 2 horizontal lines, parallel lines, 2 horizontal parallel lines of equal length. And no, when we see it, we have to say is equal to. If we speak in English, if we speak in French, we have to say égala. If we speak in Spanish, we have to say es igual. If we speak in Latin, égale son. Okay? When we see this symbol is equal to. So again, to emphasize, mathematics involves a lot of the conversion of words to symbols. The numeral symbols, the famous numeral symbols that we know. The origin of the equal sign is credited to the Indian mathematics. The origin of the numerical symbols, not equal sign, the numerical, that has to change. There's a little typo there. The origin of the numerals is credited to the Indian mathematician. Okay, Indian mathematicians. The Hindu-Arabic numeral set of 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. When you see it, we have to read it and we say in words. Okay. If we see O-N-E, we have to say 1. If we see that line, we say in 1. Okay, words to symbol. That represent the numbers in the decimal number system. They originated in India in the 6th and 7th century and were introduced to Europe through the writings of the Middle Eastern mathematicians, especially Al-Khwarizm and Al-Kindi about the 12th century. All right, so why is the Romans and the Europeans using the Roman numerals, the vertical slash and the V and the X and those things there? The Indians and the Arab, the Eastern cultures, Arab and so, were using these symbols. All right. These symbols were designed via the rule of counting the number of acute and right angles created. So the number of acute and right angles created, this is what guided the creation of the symbol. So the whole idea is you look at you perceive your environment, you quantitatively and you counting automatically, and you want to express this, what you're perceiving. So you create a system now. It's a language to communicate what you're perceiving, because you continue perceiving quantitatively. So instead of writing strokes to create one symbol, but the whole idea, the whole counting is still ingrained in it. There's a symbol that has no acute neither right angle. So it's a circle. And actually the Indians and I think the Mayans are credited for the originators of the use of the concept of zero and the symbol for it. Okay. This symbol now has only one acute. So you count in, but the symbol has been created to identify that it's only the quantity is only one, which of course now instead of a vertical stroke, then it also has a vertical aspect, but you can see the one angle. This symbol looks like our Z, but you can see there 1, 2. We calling it 2, deux in French and so forth. Trois is 3. 1, 2, 3. Okay. Let's come back there. Yes. Right. 1, 2, 3. And you can see now these symbols now, look at how they evolve. They become curved because language evolves with time. So the symbols have evolved too. But you can see the basic shape. They are very similar. The four angles, there are 2 right angles and 2 acute angles. The 5, 1, 2, 3, 4, 5 right angles. The 6 right angles, and you can see the shape. So you count in 1, 2, 3, 4, 5, 6. The 7, and you can see it resembles the 7. 7, you have 1 right and you have 6 acute. Oh, but this one is not an acute. So you can have 1 angle there that is not acute. So it's not just acute and right. So all this has to be updated also. But you can see the whole idea. Okay, so just the 7 that has an obtuse angle which is greater than 90 degrees right there. Okay, so we have to change that to angles, the number of angles to encompass acute, right, and obtuse. And no reflex. Well, oh, look, you have some 2. You have 2 obtuse there. Okay, look, you have 2 obtuse there. So it's not just acute and right. So we have to edit that. So that is why now that's another example area where you can edit what you have written and anything that you see in the internet, prepare to watch it with critic. Even here, look at here, you might have this angle can, if it wants to, be greater than 90 degrees. But the whole idea is 1, 2, 3, 4, 5, 6, 7, 8, 9 angles. All this one, all for the 9, they are all right angles. So you can see the whole idea, the whole counting activity represented in one symbol. Instead of having to write strokes, vertically strokes. When you 4, you have to write a V and so forth. Here you have, and it's this symbol now, this system we adopted now that gain precedence, and all the other systems, are not officially in use anymore. And as you can see, the whole concept of words turning to symbol, 3 plus 4 is equal to 7, and we call it mathematics. So the whole idea is from words to symbols. Here are the words. Here we have the words. 3 and 4 is equal to 7. That's English. Mathematics. 3 and 4 is equal to 7. Mathematics. From words to symbols is a translation. This we call that a language, Latin, French, and English. This we can call that a language too, mathematics, because the information being conveyed is the same. The whole transfer, the whole communication of information and writing it in words and writing it using symbols is the same information that is conveyed. So in that regard, we can consider mathematics as a language translating from whatever native language that we speak using words, the translation thereof to symbols. Yes.